Hello, everyone. Good morning and Ramadan Kareem. Thank you for joining us today at Emirates Green Building Council's technical webinar on the topic of energy modeling of net zero building. I'd like to give a special welcome to all our EmiratesGBC members and partners who will already be familiar with our activities and monthly technical workshop. Today is the second edition of our monthly technical workshop with health and safety the most important priority to EmiratesGBC. We have temporarily moved our workshops online due to the global health situation and COVID-19 pandemic. Just before we begin, let me introduce myself. So my name is Jason John. I work as the technical engineer for the Emirates Green Building Council. I would also like to welcome all our non-members who might be attending an Emirates GBC event for the first time and will provide a short introduction. So Emirates GBC is a non-profit membership organization that was formed in 2006 to contribute to the UAE's goal to be a global leader in sustainability in the built environment. The Council brings together organizations which share our mission and serves as a platform for collaboration and knowledge sharing. We run an education program with events and trainings throughout the year aimed at raising awareness of green building practice and providing the knowledge and skills to build capacity in the UAE. An important platform in the program is the monthly technical workshops dedicated to knowledge sharing in the green building industry. The workshops are facilitated by EmiratesGBC and are designed to address the challenges and share best practice and solutions on various topics relevant to the building industry in the UAE. They're completely educational and don't include sales or marketing content and are aimed at providing platform for discussion and networking. The technical workshops are generally open to EmiratesGBC members and partners only, but however, we have opened up this webinar to all parts of the industry as a wider topic on net zero buildings presented by the EmiratesGBC Net Zero Center of Excellence. The EmiratesGBC established the Net Zero Center of Excellence in 2018 as a think tank and accelerator to advance the net zero global movement here in the UAE. So before I introduce today's facilitators, here are a few practical points to cover for the webinar. We aim to keep the webinar as interactive as possible. So throughout the webinar, you can submit your questions using the question box on your control panel. The EmiratesGBC team will be monitoring and we will try to answer any logistical questions directly. All other questions we'll direct to our facilitators during the Q&A session towards the end of the presentation. Throughout the webinar, there will be some polling questions as well. So we're just going to have one just kick off right now. So I would like all audience to answer the polling question that comes up on screen just in a moment. So let's have the polling question start.
There's a small technical issue with the poll, so I think if we just move ahead.
All right, okay, no issues. All right, so without further ado, let me just. So after the webinar, we'll be sharing the presentation and recording to all the participants here who have joined us. I would like to ask everyone who's attending this call right now to fill out the survey that will be sent out towards the end of the webinar as well. So please do fill out the survey. This will help us to improve our future events. And finally, keep us engaged on social media and post using the hashtags EGBC webinars and hashtag Let's Get Technical. And lastly, if you have any questions related to the technical workshops or what the Emirates Green Building Council does, please do not hesitate to contact us using the email address that's currently on the screen right now. You can also visit our website if you would like to know more about us and what we do, and other ways in which we can collaborate, and also our future events that we'll be running throughout the year. So, to introduce our facilitators for today, we have Farah Naz, who's our Sustainability and Innovation Leader from Buro Happold. Farah is a chartered engineer registered with the UK Engineering Council and a CIBC Fellow. Her work encompasses sustainability strategy for building and city-level urban planning, as well as resource-efficient design strategy and health and well-being agenda for smart cities. At present, she heads up the sustainability and innovation for Buro Happold Middle East. Our second presenter for today is Mahavir Shah, who is a mechanical engineer for Buro Happold. He completed his master's degrees in computational fluid dynamics in 2011 from Cranfield University, UK. Mahavir heads the global design focus group for our UAE business at Buro Happold. His projects include KA Care, Expo 2020 Sustainability Pavilion, via headquarters, Four Seasons Hotels, and Gadan 21. So I will be handing it over right now to our first presenter, Farah. And
good morning, everyone.
Farah, you should have control.
Good morning, everyone.
Good morning, Farah.
Can you hear me? Okay, perfect. So good morning, everyone, and welcome to our webinar on energy modeling of net zero buildings. Before we start the main conversation today, I would like to take this opportunity to set the context and the background for today's presentation. Jason, do I have control?
Yeah, you should.
Can you change the slide to second slide while it's getting sorted? So the construction sector is one of the largest in the world economy, with about 10 trillion US dollars spent on construction goods every year. And the UAE construction sector is worth 1 trillion US dollars. Currently, there are 420 billion US dollars worth of projects currently being undertaken in the region. But globally, this construction sector is also responsible for 39% of global emission from buildings and construction works. This 39% includes building operations, which encompasses 28%, and construction itself, 11%. So what is more interesting is within this sector, 28% of the carbon emission is from the HVAC system. This sets the business case why, when choosing building HVAC systems, we as building environment professionals need to be mindful in system selection and potentially choose an energy efficient system. Now, the question is, why is this important? The 2100 climate warning projection shows that if we continue as business as usual, especially in the construction field, by year 2100, we will experience a 4-degree centigrade temperature rise. Currently, we are at year 2020, and the carbon emission in the atmosphere is 50 gigatons of CO2 emissions. The UN Climate Action Summit officially confirmed in August 2018 that 1.5 degrees centigrade temperature is socially, politically, and economically safe limit, with a roadmap to zero energy by 2050. But by year 2030, to remain within 1.5 degrees centigrade temperature rise, scientists are advising that we should be reducing our carbon emissions by 65% or more. So 2019 was a very important year for some of the significant climate milestones. This was a year where a global climate strike was held in September of 2019. This was first time in the history of climate movement. The UK architects declared climate and biodiversity emergency, which means that 925 signatories as it stands today, they all signed up to raise awareness, advocate faster change, adopt mitigation principles, and going forward, adopting the principles of net zero design aspirations for most of their projects. And finally, it's a collaborative approach industry-wide to ensure that the designs that we're designing for today's world goes beyond the standard of net zero carbon in use. 2019 was also a year where UK became the first country to declare climate emergency as a law, which means UK are committed to an 80% reduction in carbon emission from 1990 levels. Some UK cities and councils have already formed a carbon zero 2030 plan, which is highly encouraging. And companies like Microsoft have signed up for carbon negative by 2030 pledges. So this is a global overview of what's happening across the world on this topic. Now, as a business, Buro Happold, we are committed to a climate emergency ourselves by signing the Engineers Declared. We are also one of the few signatories to sign up for net zero commitment with World Green Building Council. And as a company, we made two main pledges. First, we aim to be net zero carbon for our own business operations by April 2021. And secondly, for our target is for all new projects will be net zero carbon in operation by 2030 and all projects by 2050. So now globally, beyond Buro Happold in this region, there are a lot of movements happening. In 2018, the World Green Building Council launched the net zero commitment. Emirates Green Building Council is pioneering and driving the net zero agenda in the region. And as I mentioned before, UK was the first major economy to sign up a net zero emissions law. What is also interesting in UK is UK Climate Emergency Design Guide was issued January of this year by a collaborative initiative called London Energy Transformative Initiative, LETI. It's a network of 1,000 professionals, all voluntary group who came together. It includes developers, architects, housing associations, planners, contractors, and facility managers to identify guidance for a net zero transition for their buildings and housing stock in the UK. I will show very quickly the roadmap that they have identified, starting from 2020 to 2030. And one of the key points identified was that most of the consultants and professionals believe that UK is able to reduce significant percentage of emission by 2025, more than 65%. Now this sets up and concludes the context and the background for today's presentation. I would like to take this opportunity now to discuss what we are covering in this presentation today. So today's presentation does not cover how to set up a net zero energy strategy or key design principles for net zero buildings. It doesn't cover materiality or passive design or biophilic design principles or health and well-being or the business case of net zero. But if any of you would like more information on these, please email us separately and we would be very happy to support and send you information. The focus of today's presentation is very specific. It's a technical aspect of net zero design of buildings specific to net zero energy modeling. And we're focusing on how to undertake net zero energy modeling, the techniques, the key principles, process, methodology, the do's and don'ts, lessons learned, best practice solutions, And finally, the mindset, the thinking and the responsibility of key stakeholders in order to undertake and support a net zero energy journey for a whole design team. So now I will hand over to my colleague Mahavir, who will walk you through the journey of a net zero energy modeling of a building.
Thank you, Farah, and a very good morning to everyone attending. I hope you're all safe and well. So, as Farah mentioned, this is a problem. The amount of CO2 in the atmosphere is going up, and we need a solution. What do we do at this point? The normal approach has been or is towards carrying out some analysis, maybe through Excel. Someone tries to do something very quickly, gather up an estimate, and then throw PVs or wind energy, or you buy renewable energy certificates to offset the energy. And this cannot be the approach. And the reason why it cannot be the approach is because it is not mathematically sound. And we need to have a mathematically sound approach to the problem. There's a quote by Einstein that says that you can't use the same problems, you can't use the same thinking that you used to solve the problems that you used when you created them. So we think that energy modeling is an alternative where we can use a sort of mathematical approach towards understanding how your building consumes energy. Jason, do you have control now?
Yes, you should have control.
Okay, let me just try this. So then you'd want to ask the question, why energy modeling? Well, the three main points about why we feel energy modeling is actually quite useful. The first is that it provides evidence-based design thinking. What that essentially means is that it's not guesswork. The assumptions and the design inputs that you feed into creating the model actually are realistic to the design that you have proposed. There isn't any guesswork involved in it. So yes, your assumptions are effectively guesses, but at least you can test them out. Which brings us to our next point, that it gives you data that you can analyze, you can test, you can refine, not only as your design progresses, but also as you move into operation of that building. So you could have an energy model that you could keep refining, and we will come back to this point later in the presentation as well. And lastly, it allows testing of multiple scenarios and aids the decision-making processes. So if you arrive at an energy scenario, but you wanted to test out what happens if, then energy modeling gives you a very quick way, especially after it's set up. I mean, most of the effort goes into setting up an energy model. And these are the points that make it really useful, in my opinion. So coming to the next step. So is it stuck, Jason? Who needs to contribute to the process? Well, you might wonder that, okay, so this is specific to modelers, and maybe modelers need to do all of the heavy lifting here. Well, actually, it is a collaborative process amongst all the main contributors in the construction process. So starting from designers to the clients and end users and even facilities management all have a key role to play. So for example, designers have to ensure that designs are centered around a net zero philosophy, choices of systems, materials, design criteria, all chosen to enable net zero design to be achieved. They also help modelers, they give advice about what the system is, explain what the context is. Modelers are, you'd imagine, are key to this because they have to be able to drive the process and coordinate all this information that they're receiving. They need to have the ability to analyze data and drive efficiency by making suggestions to the other parties in terms of what they need to design. Then you have the contractors. Contractors are key actually as well, because once the project goes onto site, then contractors really drive how it's built. And a lot of net zero building relies on very high quality of construction, by ensuring that they fully comply with the specifications, by complying against the energy aspects of the specifications, and they really contribute to making sure that this process happens. And also, usually in this part of the world, commissioning agents are under the contractors, so how the building is commissioned is a major factor in achieving an overall net zero building. End clients and users, so the developers, the people who use it are responsible for driving and direction and impetus. So no one's going to get a net zero building if it doesn't come from the top down, that the client wants a net zero building. So they usually make the key decisions. But more importantly, if a developer or a client has data from other buildings, then sharing that data with the modelers and designers ensures that the assumptions are more sensible and can be tested much better. And again, this is another point that we will come back to at the end, because these are all repeating themes. And finally, you have facilities management teams who, they operate these buildings. They understand how the operation works. They know what the nitty-gritties are, and they're the ones who will manage and track the net zero progress of the building. So they will set KPIs, energy targets. But again, modelers, through that energy model, those targets will be set, and then they are refined. So you can see that it is not an isolated process. It is not the modelers going away. And in fact, the more that happens, that everyone works in a silo, the less it becomes possible for a net zero building to be achieved. So going to the methodology, this presentation is basically divided into 5 parts. We want to decide the approach. We want to look at how we set up models. We want to talk about operation profiles and why they're important. Then we want to touch upon analysis and certain energy uses that you don't actually consider sometimes, but you should. And lastly, it's about closing the loop. So you've done the analysis. Now, what do we do next? So the methodology can also be summarized as a process. I mean, this is general to any energy modeling process, or it's effectively useful for if you want to do compliance modeling or net zero modeling, or just simple modeling that you want to test the energy efficiency of your systems. So you start off by designing the brief. You want to understand the context of why you're doing this. You gather the model input data, so you'll have data from the MEP designers, from the specialists. You gather it. You then proceed to physically create, to virtually create the model in any chosen platform. Now, I mentioned here that the presentation doesn't touch upon any particular software, although you'll see examples mainly from IES, which is what we've used. But this applies to HAP, Energy Plus, IESV, Train, Trace, any software. You then set up the HVAC system to the capability of that software. You define the operation profiles, you carry out the analysis, and there is a step of refinement. So depending on what you're trying to achieve, you carry out refinement runs, iterations, and once you're satisfied, you go and you close the loop. So starting with deciding the approach, you have to ask yourself a few questions before you start off. The first is the modeling being done for compliance or for net zero? Now, I'll explain what compliance modeling is in the next slide, but we just need to check what are we going for. And there's slight differences between going for compliance modeling versus going for net zero. If net zero is the target, then do we need to balance our peak energy consumption or annual? Again, I'll explain this in the next slide, but effectively we need to decide for what. If we are providing PVs, then how much PV we need to provide, or any other renewable energy for that matter. And for compliance modeling, what is our target energy offset? So understanding peak versus annual energy usage, you might have seen these graphs before. Basically, if you plot the energy demand of a building over a whole year, you see a graph like this, especially in this part of the world. you'll see that the energy demand peaks in the summer as air conditioning demands are quite high, and towards the winter the demand falls quite significantly. But what people do understand, but they sort of and they know, and designers will know this, and they will work towards this, but they won't actually calculate this, is the actual effect of part load. And what that means is that the annual peak demand is probably 1, maybe 3 or 4 points in the year. So in the graph, if you notice, the peak and nearly peak energy demand is within a small band of months between, say, June to September. And this is something that we know traditionally for this part of the world. However, if you inform your model properly, you realize that even during summers, at say, for example, nighttime operation, or on weekends, you'd have situations where the building energy load is quite different from the peak. So this could be about a 50 to 60% drop off in energy consumption. And this is true for even the off-peak months, where the peak part load is probably only is only about 50 to 60% of the peak load. So what that means is that the building actually operates in a part load condition for maybe 90 to 95% of the time. So it's important to know, if you provide enough PV to satisfy the peak demand, then you'd actually end up with a net positive building. However, if you want to make sure that the building is net positive or zero energy over a given year, then you don't necessarily need to provide enough PV to satisfy the peak, but you'd ensure that you'd ensure through the calculations that you've satisfied the sum total of all of this energy in this graph. Now, an important point is that if you do go down that route, then you have to convey to your clients that you'd still need grid energy connections, because when it comes to peak, your actual peak or actual PV usage could only be possibly a single line that way. So that's why you need to understand about the peak versus annual energy usage, because that helps you determine what path you want to take. The second one is about compliance. Now, compliance modeling, what I call compliance modeling, is any modeling that you'd carry out to satisfy something like to obtain a certification such as LEED or ESTIDAMA. And typically you'd follow the ASHRAE 90.1 Appendix G pathway. And the difference between net zero modeling is that ASHRAE 90.1 is Appendix G, as an example, is compliance based, is prescriptive. So there's a certain set of rules that you need to follow, and you'll probably end up setting up your model that way. And you normally look at you take your building and you apply it to a baseline, and then you take your same building and then you test how much your energy differs from that baseline. So the presentation doesn't actually go into compliance modeling, because that could be a separate presentation all on its own. There are a lot of fundamentals about how you actually go through the 90.1 process. But regardless of what approach you take, nothing should stop you from determining the energy consumption of your building. You can do it regardless of what method you use, as long as you understand what you're doing and what inputs you're putting in. Which brings us to a second part of our presentation, which is actually setting up the model. And you start up setting up the model by doing the first thing, the geometry. Now, depending on whether you use, say, HAP, where you define it by text, or you use IES, where you draw it graphically, as a modeler, you need to understand the building, the geometry, the form, and the orientation. Now, let's assume that the form, orientation, and the building fabric has already been decided by the designers and has been designed to reduce energy consumption. So it's effectively been designed with net zero in mind. You need to ask yourself a few questions. So the first one is, how much does the building form contribute to the overall energy consumption? Now, understanding this, it means that if your facade has been designed with net zero principles in mind, then you are already reducing the amount of energy or the heat gains to the facade. So the cooling energy demand due to facade gains would already be quite minimal. So you need to understand that's the first question. The second is through your software. Can your software that you use actually represent the geometry accurately? So certain softwares might not have that sort of range to be able to accurately define, round curves or circles or something like that. So take HAP, for example, which is text-based. So you put in the areas, you put in the facade, wall lengths, and so on. And the third thing you have to ask is, do complex shading structures, you often see mashrabiyas in this part of the world, do they actually need to be modeled as geometrical elements? Again, going back to the first question, what sensitivity is there to the overall energy consumption? If you look at the picture on the right, you'll see the Westminster, the Houses of Parliament. Now, if you take that as an example, and just use it as an exercise, so what elements from those you would consider absolutely necessary versus what elements you would consider as a like to have? And then you would start off by saying, well, I definitely need the glazing. I need the windows to be there in the right position and with the right orientation. But some of the roof elements, the spires, the decorative work on the facade, I could ignore because that's not going to contribute to the energy consumption. So it's questions like those that you need to ask yourself through this process. Because understand this, energy modeling is an iterative process. Heavy geometrical models increase the modeling times significantly. I've had a couple of projects where I've done heavy models, and it was an absolute disaster to work with. You not only get a lot of geometrical errors, but sometimes the complexity causes models to actually give unrealistic results. So there's no point in having an extremely complex geometry to represent your building almost perfectly right and not being able to get your outputs on time. This has to be a process where it is repeatable and should be easy to do. Then you come to setting up the thermal criteria. Now, the idea about the thermal criteria is, and this is already done as part of the basis of design, what you need to do is within the model, try to group them as possible, provided the model, the software platform has that capability to do so. The advantage of doing so is that when you do want to analyze the results, you can easily analyze results by energy consumption from different space types. So for example, if you have an office building, and you wanted to see the energy consumption of interior offices versus exterior offices, if you group them that way within your platform, then you should be able to analyze them separately and then make decisions. It adds another depth to your modeling process. But at the same time, you want to simplify this as much as possible. You don't want to create so many space. You don't want to create so many space types as there are spaces in the model, simply because it's difficult to manage. And then we come to the most important part of modeling, and that is setting up the HVAC systems. Now, HVAC systems are really important because, as you saw from the graph, the building load is variable, it's dynamic. And as the building load varies during a day, during a month, during a year, you need something. The HVAC system also varies. Now, as you saw in the slides earlier, that HVAC systems contribute to a lot of energy consumption in the building. So it is really important that we set up HVAC systems to mimic the real world design as closely as possible. You should model all system components, and all parameters should be modeled. So for example, if you have thermal wheels in your air handling units, you model the sensible latent effectiveness, the power consumption, you'd model the coil sizes, you'd model the pump power efficiency, the efficiency, the part load curves. And I want to point out chillers here. So especially if you have a chiller system on your project, then trying to get that part load data of how the chiller will work at different temperatures and different ambient conditions and different load conditions can make a very big difference to your final energy numbers. So we've seen this on a couple of projects as well, where we started off by just doing static analysis on peak COPs and just extrapolating that for the rest of the year, and versus when we actually gave proper part load curves. And when we started giving part load curves, we saw that the energy demand dropped significantly. It became more efficient. Now, that wasn't to say that that was unrealistic, because that is how the chiller is going to perform in real life as well. So we want to bring a degree of realism to the whole process. So the bottom line is that as much data is available, you need to put that in. And depending on when you're doing it, if you're doing this during design, then you would want to use material equipment selection data from mechanical or electrical schedules. However, if you're doing this during construction, then as the contractor submits material submittals and these are approved, you can start using that data. One of the things that I've not written down here but is important is log all your data. Whatever data you get, whatever assumptions you use, make a log of that, because ultimately when you carry out your analysis, you'll need it. So over here you'll see, So over here you'll see a sample HVAC system that we used on a project. What this is basically an air handling unit, fan coil unit system. And as you can see, I've just marked out. So that component is the heat recovery wheel, the cooling coil, the supply fan, the second heat recovery wheel. We've got the heater batteries, the fan coil units, the fans. We've got all the components laid out over there. And at the same time, in the chiller, if you see in the next dialog, the chiller in all the parameters that you use for the design of the chill water system. So be it if there are any condenser pumps, then you use that. You use the building total chill water capacity of the chiller. What is the supply temperatures? What are the outdoor temperatures for design? So you want to define as much as possible, and this is where you inform the model. The more data you put in, the more realistic your output becomes. So then you have to set up, the control systems as well. And you want to inform the control system. So for example, for each space you would have, if you had a fan coil unit, then you would want to control, and this is in actual conditions as well. You want to control the air temperature, you want to control the heater, you want to control the room humidity through control of the air handling units, and you want to control any fresh air VAV boxes if you have demand control ventilation for your space. And you need to define each of these controls for each of these spaces, right? So you want to replicate the control systems as closely as possible, and you want to mimic the actual BMS design wherever you can. And if you don't have the controller, then you can obviously ignore it. And this is where I would bring a few words of caution. Why is all of this so important? And what can really go wrong? Because HVAC systems are fundamental to proper energy system design, so energy calculations. Well, most of the errors stem from incorrectly defining the HVAC system. In worst case scenarios, your models will refuse to run. In best case scenarios, you'll get unrealistic results when you put in the wrong information. And usually happens when the modeler does not coordinate with the designers. This is why I come back to the responsibility of the modeler. The modeler needs to be able to talk to the designers, coordinate, and understand what he or she is setting up within the software. A number of errors will creep into the model setup process. It's bound to happen when you deal with a lot of data. It is going to happen that you will have errors within your process, and these are and it is going to happen. So you need to be careful about this. Keep checking as you go along. Without accurate model inputs, the outputs are no longer reliable. So you could set up the model, you could put in all your inputs, but if you inputted them incorrectly, that's it. You know, a common saying is garbage in, garbage out. That's exactly what you'll end up with. Then it is important to understand that different inputs have different sensitivity to the output, and you need to understand what the sensitivity is to decide what is important. So for example, if you have a parameter that controls a heater battery off coil temperature, then you might decide that the heater is not going to come on very often. So does that actually matter? Maybe not so much. Maybe you set a parameter as 35 degrees for the heater output, but it never actually gets there. So you need to decide what's important, and modelers need to be aware of what information they require prior to commencing modeling. The biggest risk is not knowing what you will need and why you will need it. That is very key. So you need to start off with understanding that. Which brings us to operation profiles. And the reason why operation profiles are so important is because building energy consumption is mainly through usage. So up till now, you've set up a system, you've set it up, all of it is static. There's nothing dynamic about it. But the usage profiles bring the level of bring the dynamism into the model. And there are two types of profiles. You have the space and building operation profiles, and then you have the system operation profiles. Space operation profiles define how spaces consume energy or generate heat. This is true for cooling systems. Space operation profiles also include profiles for things like temperature, how the space temperature varies in a day. Humidity in a given space needs to vary in a day. So for example, we've done a greenhouse where the humidity needs to change from time to time, where CO2 needs to, where you have demand control ventilation, or maybe you have setbacks for the ventilation system. So for example, if you have a trickle and boost system for your toilets, and at the same time, system operation profiles are mainly define how the whole bulk system will react. So this is at a system level, at the main air handling unit level, at the main chiller level. But it must be noted at all points, both the profiles need to be in sync. You can't have system profiles that say something and space profiles that say something else. They both need to match. So why are the profiles so important to the process? Again, profiles determine how the building operates. Not enough thought goes into defining these. We generally, as we do HVAC design, and because we design mainly for the peak, we never think about it. For us, the peak load of a space is a flat line that goes on throughout the day, and it doesn't really matter. But we need to have more thought when we define these for energy models. At the same time, not enough data is available on building operations. So if you try to research this out, and you try to look at the number of research papers that actually show realistically how a building or a space consumes energy, there are very few papers available on this. Even ASHRAE only touches upon a few typical spaces, such as offices or hotels, where they know, or at a bulk level, what the operating profile for these spaces is. However, you can be a little relaxed about this, you can be a little relaxed about this, especially when you're doing compliance modeling, because the compliance modeling requires baseline and proposed operation profiles to match in most cases. Also for spaces where the sensitivity is not so high, you might have a storage room where the load is only, say, 100 watts, and it really doesn't matter. So for those sort of spaces, you could sort of be a little relaxed, not have to think about operating profiles as much. So coming to the next point is diversities. Now, along with, you need to understand the usage of the space, obviously, and how it operates. Both are very crucial points. If you look at ASHRAE fundamentals on the chapter about non-residential cooling, and there's a lot of data about office equipment, and primarily the research suggested that actual power consumption is only 50 to 75% of the peak nameplate power. Now, this data is available for a lot of office equipment, but as you go on, it's not available for a lot of things like pumps, for chillers, for non-standard equipment. And especially we come to this, kitchens, server rooms, digital projection cameras, those sort of things. No one really knows it. So you have to almost extrapolate it from this point. You have to make assumptions. And when you decide diversities, you should incorporate all such considerations and usage factors, and then build your final operation profile. So your operation profile will include all your diversities, all your usage factors, and you have to be careful about this, because if you choose unrealistic diversities, you'll get unrealistic results. So let's start talking about, let's look at a few profiles now. We can define profiles for simple spaces fairly accurately because there is information available. So if you take an office profile and you look at the power usage, you'd see as people start coming in, maybe for an office that works from 9 to 5, people start coming in at about 8, and by about 9 o'clock, everyone's there, 10 o'clock, everyone's there. Then you'd see around lunchtime, between say 12 to 2, there's a dip as people leave their desks to go lunch. Maybe 30–40% of the people will leave the office. And then at around 5 o'clock, you start dipping and going towards the end. And there's a base energy consumption that probably results from computers being on standby mode, server racks, that sort of thing. The lighting can also be defined. So if you have an office with daylight lighting and dimming, then you'd probably see that as the people come in, then the usage becomes higher. And once it gets really bright, the daylight dimming kicks in, and it goes, and the lights dim, and then again rises up, and again goes back down to say 20%, which is maybe you might only want the perimeter lights to be lit. And these profiles are generally held to be accurate given how offices operate. So if you had you had an office building with office spaces primarily, and you use these profiles, they would be more or less accurate. But if you start coming to some non-typical spaces, non-standard spaces, they become much harder to define. So consider, let's take the example of a server room, right? And a server room would typically have security racks. They'd have telephone switch panels, data racks, network servers. How do we actually define the usage? Security racks might be operating full time because they control CCTV. Network servers might be operational during office hours. Telephone panels might be under more stress during office hours. Data racks need to be backed up at all times, so they might be operational continuously. If you assume that, let's say that the total kilowattage of the total power consumption of the server room is 22 kilowatts, and if you assume that it works at 100% for the full year, then that 22 kilowatt translates into 175 megawatt hours of energy consumption per year. And that's massive. That's just 22 kilowatts. If you have a good office building with say 10 times that, then your energy consumption is around 1.7 gigawatt hours. And suddenly you start getting into massive load territory. But the question to be asked is, will all the systems operate this way? And is assuming 100% operation even correct? The answer is that no one knows. There isn't any. From what we looked at, we haven't found any data that governs the operation of IDF rooms. And especially when you're trying to look at savings, when you're trying to look at how to achieve net zero or to drive energy efficiency that 1% more, then it's hard to ignore IDF rooms as potentials for savings if you can only understand and inform these better. Similarly, you could look at another space type. You could look at commercial kitchens, and the funny thing about commercial kitchens is that they have high peak or nameplate loads. Most kitchen equipment, especially if you look at say combination ovens or electric stoves, they would range in the 5–10 kilowatt capacity range, but they don't necessarily give out heat at the same value. The usage of extract hoods, also changes the way heat is generated in the kitchen. So it's never one-to-one, and you need to understand that as well. But going back to the kitchen equipment capacity itself, it's not going to operate at full load for the whole duration of the kitchen operation time. You might find that in some cases, the preparation areas are more in use during the early part of the day. So all the equipment associated with the preparation areas is used for 3-4 hours at the beginning of the day, and then everyone moves to the cooking area. The same way dessert stations might be towards the end of the day rather than the early part. And so it's not a peak load where everything is in use at once. So again, for the projects that we did, I actually ended up defining the operation for each and every piece of equipment, trying to allocate a certain usage time to each one. So if there was a if there's equipment used for vacuum packaging of food at the end, our assumption was, hey, this is probably going to be used at the end of the day when they want to pack everything up, and so it might be used for at the most an hour, and that actually helps because then you'd see that your actual energy consumption is lower than what you would if you assumed 100% operation. Dishwashers, as an example, might not be operated continuously. Dishwashers might be operated at a few fixed times during the day. Again, like IDF rooms, there isn't any data available, sadly. So the only way to improve this is by getting more and more data. As more and more people do this, and as more and more people try to test their assumptions in real terms, this gets better and the assumptions get more refined. So to summarize this, if for all spaces we need to determine the most realistic usage patterns. We can take more examples. In a storage room with presence detectors, realistically the lights will be off 90% of the day. So why would we want to simulate them as being on for, say, half a day? If you provide equipment provisions in back of house corridors, those let's say you provide plug points. Those plug points are not going to be used for anything more than cleaning or for temporary equipment. Understanding this from the FM teams as to why or how they would be used would help inform this. So instead of allowing equipment consumption at 80% for the whole day, you'd say, well, it's 100% for 2 hours, which is actually less than assuming 80% for the whole day. And it doesn't matter. At the beginning, it won't, for certain spaces, it doesn't really matter where this happens, but you can actually assign times of day as well in your profiles. Toilets in private areas will have a much lower usage profile than toilets in public areas, which is obvious. Auditoriums, you won't use auditoriums continuously. They'll have short bursts of peak energy use, but close to zero when not in use. So you can, for example, make an assumption that you can start by asking yourself how many shows there will be, how many times per week the show is going to be, and what is the energy use per show. And even that's enough. It doesn't need to be an energy model in this case. So you can still do it by hand, but as long as you're making the right assumptions. System profiles, I'm going to touch upon this very quickly because it's mainly about setting the bulk system operation. So is it on, is it off, when is it on from, when is it off from? And the only thing that you need to remember in this is that it should not clash with the space profiles. So if you've asked your space to set back at night from 24 to 27 degrees, don't tell the system to switch off. So that causes problems. So let's take the example of a retail mall, and let's start by understanding what space types there are. So in a retail mall, you'll have retail shops, you'll have anchor stores, you'll have arcades, entertainment areas, you'll have cinemas, you'll have food and beverage, you'll have back of house areas. So those could be offices, corridors, MEP rooms, storage rooms. You could have front of house areas, so corridors, prayer areas. Now, typically within the UAE, the mall operations are normally from 10 a.m. to 12 a.m. So already your profiles need to account for that. You could argue that FM staff usually come in at 9 a.m. to start cleaning the premises and then leave by 1. So again, that needs to be factored into your profiles. Prayer rooms, prayer rooms have 5 main peaks during the day to coincide with the 5 important prayer times. But 1 or 2 there might be outside operating hours. So 2 of the peaks will fall outside the operating hours. Cinemas normally peak around 7 p.m. to 12 a.m. and around those shows. This is not to say that cinemas won't have occupancy during the earlier parts of the day, but you could almost factor that in and sort of adjust the profile accordingly. Food and beverages would peak at 8 to 11 p.m. normally, and usually tails off towards 12 a.m. You'd have, this could be different on weekends, by the way. On weekends, you could have it more continuous. You could have a peak at between 12 p.m. and 2 p.m. as well. The behavior of retail shops and anchor stores is pretty much the same in terms of profile. So you don't really need to create a different profile for them because they have the same operating pattern. But here's an interesting thing. If a mall has a specified capacity of let's say 100,000 people, or let's say 10,000 people, a given visitor can only be in one place at a given time. So there is a need to somehow be able to distribute occupancy in a sensible manner. And what that means is, if you have 10,000 people, not all 10, you won't have 10,000 in one shop and empty everywhere else, because that skews your energy numbers as well. So what can we do to understand that distribution? Well, can people flow analysis help? Now, people flow analysis is basically a method wherein it's a social analysis method wherein you simulate the movement of people as they interact with their spaces, and there are certain rules about it. So if anyone's interested, and please reach out to us, and we can share more information about this. But what it does is effectively, as you can see in the image, it shows you where people will congregate and why they're. So that's probably a reception desk where people are all congregating around. You have aisles or F&B areas where they sort of spread out towards. And through analysis like this, you can determine where people are going to be at a given point of time in your mall. So I think if you have access to information like this, then please do use it for your analysis. It will help massively in giving realistic numbers. So then we come to part 4, which is analysis. So you've set up the model, you've set up everything works, you don't have any errors with your systems, and everything's great. You get your first energy usage numbers. The first step requires you to understand the results in relation to the assumptions. You have applied assumptions to your model. Essentially, your design parameters are watts per square meter for lighting, watts per square meter. Are they realistic? Are they going to operate that way? Start by breaking down the results by each energy demand. So chiller energy, your energy for running fans, energy for cooling. Start by breaking it down. Understand where the energy is coming from. Is it from power? Is it from lighting? And do it for every space type if you can. Benchmark this against any baseline or any other parameters or any other precedent projects that you've done. It will help. Quantify the impacts of operation profiles and inputs to the obtained energy figures. Start by looking at your profiles. Look at your energy numbers. Do they make sense? Are they when looked at collectively as the whole building? Does those numbers make sense? The modeling process is iterative. You have to refine all assumptions and inputs to determine most optimal and realistic operations. The first step is never going to be the final answer. You need to keep testing this till you're satisfied that whatever inputs you put in are realistic. And in the absence of data, you have conveyed those assumptions effectively. Most of all, QA and check models thoroughly. Do not believe that your models are perfect at the first get-go, because I have seen them, and unfortunately I've learned this the hard way, that models are never right in the first go. They have to be checked, and it would help if it's checked independently by someone else. Could be another fellow modeler, but do go through that rigor. If you look at this pie chart, I mean, it explains what I'm talking about. So for this building that we did the energy model for, the big blue slice of the pie is AVICT loads, and the next big brown slice of the pie is from kitchens. So already we could tell that most of the load came from AVICT and from kitchens. Now, when we further analyzed that AVICT load, we realized that the reason why we were getting such huge loads were because we were simulating them 100% for the whole year. And so we had to go through a process of understanding diversities, trying to apply some sensible diversities. Some of these were applied through the experience of different people who had worked in the field for a long time. And we sort of came up with a slightly less intense number. We did the same for kitchens and try to apply reasonable estimates of how much equipment will be used, when it would be used, and we brought those numbers down as well. What we could see is that the rest of the building was quite minimal. So there were the rest of the building being storage rooms, corridors, offices. So I think we found this quite useful because we could quickly delve into each space type and try to understand where the energy resulted from. And we could also see any discrepancies. Really, all discrepancies stand out. You know, if you look at an office space and suddenly you see it consuming 300 megawatt hours of energy per year, you are bound to question that. So doing it this way does help. Remember that the energy model will give you access to a lot of data. Use that data. Try to use as much of that data to understand what's going on as possible. And there are certain usages that you don't consider, and these are usually true for, this is mainly towards net zero modeling. It's less impactful on compliance modeling because, again, in compliance modeling, it is assumed that equipment energy consumption in the baseline and proposed is the same. So some of those areas which you wouldn't consider are, for example, pumps for drainage, public health equipment, so water pumps, which are used intermittently every day. But these can build up over a given year. So on the same project which I was talking about previously, the public health equipment and the specialty equipment were contributing to 200 megawatt hours per year of energy consumption. And understanding that allowed us to question those numbers. Where, you know, it might be easy to assume that anything that's within the thermal line consumes energy, but you actually tend to forget about things that are outside the thermal line. So as an example, aviation lights. It's easy to forget that, you know, aviation lights consume energy. It might not be much, but unless you quantify that, you won't really know how much energy it's going to consume. From items which may be specialist entry exit gates. So if you have access control to your building, those gates, especially in a mall, those gates are going to be going up and down continuously, consuming some amount of energy. In a small project might not be of importance, but if you take something on a Dubai mall scale, you know, many entry gates, many exit points, all those consume energy. And that could also be security equipment, any infrared scanners or any sort of back checking machines. You tend to forget these. Lifts and escalators, you don't necessarily tend to forget these, but you don't necessarily tend to calculate them accurately. I know, especially for escalators, the calculations for escalator energy consumption are actually quite what's the word for it? They're quite strange to do. So, and they're quite interesting to do as well if you start thinking of, because as the escalator goes down, it consumes less energy. As it goes up, it consumes more. But doing those calculations are important. Sometimes you'd ignore parking fans, which are used only for carbon monoxide control in the parking area. So you just assume that because they're intermittent or they're not supposed to come on. And any power provided to, say, if you have outdoor exhibition areas in your plot, or any outdoor areas that you might carry out, you have given a power provision to, but you use once every month, then you need to account for all of these. All of these need to be accounted for. You need to go through the same process of defining operation profiles and diversities and calculating the energy. When you're doing net zero modeling, and account for all public holidays, account for Ramadan times for Middle East, North Africa countries, account for weekends, because all of these, if you assume that the building is operating continuously, you'd have at least 52 days of additional energy, which you really don't need. So this is an example again. What we ended up doing is to calculate the landscape lighting, we basically assigned a profile of operations saying that, okay, the landscape is going to be on at night and off during the day. We knew what the peak power usage was, so we just ended up calculating that for a given day. So each day would consume about 150 kilowatts of power, of energy per day. We did the same for facade lighting, for external performance areas. And we sort of ended up with a table like this, where we had the energy demand per day, and then just multiplied that by the number of operational days in a year, and you end up getting an energy consumed per year. Now, this is okay to do for areas which are little more challenging. Now, energy models typically will not allow you to calculate energy demand from, say, a water pump in a straightforward manner. There are ways where you can do it, but you might find that this is easier for some of the non-unique spaces. But the key takeaway from this is account for everything. Whatever you can think of, account for it, log it, and then decide if it's important or not. And once you do all of this, you've done it, you've done the energy model, you've arrived at reasonable numbers, you've arrived at a certain set of assumptions which might need to be applied to the building itself, and so therefore you need to close the loop. And so when you have to close the loop, understand that if there are any assumptions that will impact how the building is commissioned, how the FM teams or the clients are going to operate that building, do convey that, let them know. Because ultimately, what do you want to do? You need to engage with all of the stakeholders. You need to engage with the client, the owner, the operators, the contractors. It is the continuous engagement process. So Bistria, for example, has recommends something called the soft landing and the design for performance process. Maybe you could employ that. And what soft landings effectively is basically, it's a process wherein you involve you and the rest of the team, start talking about performance from an early step. You show commitment, but you adopt the entire process, which means that you start. You stay committed to having a net zero or a performance-based approach towards the building. The client provides leadership and direction. Everyone has set roles and responsibilities in achieving this sort of high performance building, which also extends to net zero. You have continuity so that the process doesn't stop at any point. It continues on from design to construction to operation. The client commits to aftercare, so there is a process of continuous improvement. It's a collaborative process, so risk and responsibility is shared amongst the team members. Ultimately, in all of this, what are we achieving? What are we trying to do? It's easy to get caught up in the fact that this might become contractual, or this might become, is this a risk to me? What if I can't achieve it? I think if we need to truly head towards net zero buildings and to reduce our carbon footprint, we need to shed some of that apprehension and move towards a goal of shared risk and responsibility. You have to use feedback from these buildings to inform new designs. And you have to set KPIs and set operational outcomes. What are you trying to achieve at the end of the day? Building operators have to be involved, and the end users have to be involved in this process. There needs to be awareness. If you're designing a net zero building, make sure that that is followed through to the end user by running awareness campaigns. I recall the example of Genzyme headquarters in the US, which was designed to be LEED Platinum. And one of the key things that they kept saying was how they kept running user awareness campaigns and making sure that people and visitors were kept appraised about what they were doing to have low energy consumptions in that building. So this is really key. You need to set success criteria and performance targets for all of this. All of this is for closing the loop. And all of this is dependent upon having good energy numbers, reliable energy numbers that you can use to build off. And lastly, you communicate and inform. Communicate openly, inform, share the word, because this is a continuous improvement process. So to summarize, energy modeling is an important tool to estimate building energy usage, and it can be used to drive efficiencies in building design principles and operation to eventually obtain net zero when you couple it with renewable energy. Believe me, it's hard. I do agree that getting to net zero is extremely difficult, and it requires a lot of improvement and a lot of effort, but it is worth it. It requires the modelers. The modelers need to understand the building systems and the inputs that define them. They have to. You cannot model in a silo. You cannot model You can't be static about this. You have to really. You have to internalize the building systems and the building operation. Your thought should always be, how is this building going to operate? Have I made the right choices for the design inputs? Close the loop with the stakeholder engagement. There's a lot of effort that goes in from conceptualization to analysis. Let us go and construction. Let us try to close that loop on every project to achieve energy success. The last two points and 3 points are extremely important in my opinion, and those are that data from existing buildings should be mined, analyzed, and shared. I think it's something that needs to happen more. It is a process of continuous refinement. There isn't enough data available on how buildings operate at the moment. We need to start analyzing space types. The more data we collect and we share, the better buildings become for the entire community. So it is a process of continuous refinement. The point in red is important. You need to accept the fact that in the first year after you build it, the performance will not match the model from the get-go. And there are a variety of reasons for that. The first one being that the assumptions could be different to how the building actually gets used. The second could be the inputs could be different. The third thing is that it just takes that much time because you need to make the users aware of how to operate the building as well. But because if you start taking it as a continuous improvement process, then you need to set yourself up maybe 2-3 years through a plan, through setting operational targets, to setting KPIs, that how you are actually going to achieve that net zero target. And FM teams are really important. So if you remember at the start of the project, at the start of the presentation, I mentioned that FM teams have a big role to play in this. FM teams have to play that role in trying to continuously drive the operation towards a net zero and try to match the model. At the same time, the model needs to be continuously improved to match the operation as well. So it's a two-way interaction between model and operation, and you almost end up converging to an optimum solution. And finally, and the most important one, analyze the data, test iterations. confirm your assumptions, optimize those assumptions, and repeat the process. That's it. That's all what energy modeling is. It's a process of continuous refinement and data-based approach. Thank you. At this point, that's it. That's the end of the presentation. And thank you very much for listening in. Jason, can you move to the next page? Oh, sorry, I can do it. Thank you. And if there are any questions, please.
Yeah, so I thank you, Mahvir, for this wonderful presentation. I think it was a very good insight into the NG modeling of the building itself. There's a couple of questions that have come in, and I've just been going through them. Let's start. One of in the previous slides, let me just start with this question. In one of the previous slides, the HVAC system modeling, what was the software that was being used, or what software do you use?
So we used IES, Virtual Environment by IES. It has a module called Apache HVAC. We use it widely in Buro Happold, but at the same time, it's my preference because that's what I got trained on. You could equally use Energy Plus, TAS is there, Train, Trace, HAP, anything. The good thing about IES, what I feel is that it gives me a lot of how do you say, it gives me a lot of control over different parameters. So hence I tend to use it. But again, I think it's important to understand, goes back to understanding the scope and the brief. I think I've seen energy models being done on HAP. It just depends upon what you're trying to do, what you're setting out to do, and how much accuracy or time you have to do it.
Just to add to that, Jason, the real idea of using an energy modeling is to have an evidence-based approach. So we should aim to make the energy model as much accurate as possible. And as a mechanical engineer, IS provides a lot of granularity and detail where we can get into. And that's why we found IS to be one of the most stronger software in this field. TAS has a level of granularity as well, but I think we should all aim to create energy models as realistic as actual building, not just an compliance exercise which doesn't really give value to the team or the project. So.
Interesting. As speaking of another question, interesting question that we got was on the operation profiles assumptions. So this question is more on the liability side. So who is liable to ensure the operations will follow the design assumption? Who takes on that responsibility?
I think that's a very interesting question. Farah, you want to go for it, or I'll go?
Yes. So, as Mahvir mentioned, it's a collaborative approach. So the first conceptual level design meetings that should be held, there needs to be a conversation happening on how realistic our sustainability strategy is and how do we take the realistic assumptions into the energy model. So from the first meeting onwards, the entire design team, the FM team, the engineers, everybody needs to be on board. Now, the operation profiles depends on the client's information as well. How would they like to use the building? So there's a lot of conversation needs to happen between the energy modeler, the design team, and the client team to make the assumptions that goes in the model as realistic as possible. So the question about justification of operation profile, if a conversation takes place with the client and the information comes from the client side, then all the assumptions could be clearly laid out in the modeling report for the future FM team to take it forward. I hope that answers the question.
Yeah, just I'll add to that. So ultimately, like as Farah said, it needs to be a collaborative process, and I think there needs to be as the whole as energy modeling becomes more prevalent, and there needs to be an understanding that that's why I made that second last point, that it's not going to match from the get-go. You won't have a model that just matches operation, because it's not. They don't. There's a lot of uncertainties in the way we do. What you have to do is try to make the best possible assumption, and everyone needs to be on board with those best possible assumptions. So the process would be one of where people advise and say, no, we don't believe that the operation will happen like this. This is what we think. Because ultimately, the important word here is think. No one really knows how these are going to work, except as time goes on and when we have that data. So the reason we know office buildings have that profile is because office buildings have been checked for those patterns. You can go to you can see research papers that show office energy consumptions, and you'll see a similar kind of pattern. The granularity of that pattern might change, so the fine changes, but at a bulk level it would still be the same. So I think that's really important to understand, that it needs to move away from, it needs to be a collaborative approach rather than one of trying to figure out this is the right answer, this is how it should be.
And one additional point, Jason, we suggest all our clients to therefore do a post-occupancy evaluation. So after the building has been occupied, we suggest that we as engineers stay involved in the process of fine-tuning the building. BizRIA in UK did a study, and they found in UK to fine-tune a building from the day of the building is occupied, it takes 6 to 8 months, because in UK they have to go through a winter and a summer. But in this region, it minimum should take 6 months to fine-tune a building, and in that case, a post-occupancy evaluation, fine-tuning of the information is really, really important, and there needs to be a collaborative discussion happening between the operations team, the client, and the engineers who have designed it. So that's kind of like feedback loop and closing the loop of the understanding.
Yeah, I agree with both of your points on this, as the energy model is only going to be as realistic as the assumptions you've taken in, and definitely the consumption profile won't be 100% accurate, but within the reasonable amount of error. Obviously, you have something. Energy model is better than going in completely blind. Another question was actually related to the topic a bit more closely on net zero building. So how can you use energy modeling to basically model in renewable energy systems to offset your consumption?
So if I understand this correctly, it's about how you use the software to model renewable energy?
Yes.
It depends upon the capability of the software. What we normally have is, usually we'll have a PV specialist who carries out their own calculations based on the available land area, or there's two ways to approach this. The first is you do your energy model, and then you can sort of determine how much PV is needed, and then you can reach out to a PV specialist who then advise how much is possible. It can happen in parallel as well. So you do the energy modeling, a PV specialist, because often with PV, the bigger constraint is area. And if there is enough available area to place the panels in an efficient manner. And so what happens is that you'd have a PV specialist doing their calculations, and they'll come up with a figure. So you don't necessarily need to model PV within the same energy model. You can have it separate, as long as it's you can do A minus B equals 0. So generation is equal to consumption, then you're good. But I know for a fact that IES does allow you to put in PV, but we normally don't do it within IES. We do it separately.
But just talking in general, if a consultant have been asked to use any kind of energy modeling, whether it's IES, Energy Plus, whatever software it is, to predict renewable consumption, the modeler needs to be very careful in terms of what assumptions they're ultimately putting in that model. As Mahavir mentioned, garbage in, garbage out. So the consultant has to really identify the assumptions, agreed with the design team and the client that the assumptions are correct and accurate in order to ensure the demand of the building is properly reflected on that energy model. And then this is a back step from the answer that Mahavir just gave. And then they can take further steps to cross-check the information. But always we would suggest a cross-checking. You would get the PV consultant to run their calculations, you would get your own electrical engineer to run the calculation, and then you run your own modeling to cross-check whether 3 levels of check kind of meet the prediction. So that's another way of thinking about this problem.
Interesting. Another couple, a few questions that we got were related to basically benchmarks or standards. So I'll just read this one question that we got. Is there a benchmark to consider people flow analytics as part of design process while energy modeling?
So people flow, we have a smarts analytics team, and the team has been collecting data on buildings for the last 10 years of every possible building typology and occupancy. And that's a benchmark data that we use currently when we predict the people flow analysis for a certain, for example, a resort. Recently, we ran a people flow analysis for the parking of Louvre, Abu Dhabi, how people flow from the parking to the entrance of the building. So it all depends on, data is very important. It's actually a data-driven design. And if people flow movement is used, either the data can come from our existing database or it can come from the client. But the key is to ask the right questions. The key is to ask what is the intention and how we are going to be using this analysis. It's fun to see a video which is really dynamic and impress the client, but what we really need to understand is why we are trying to achieve certain goals and what is the ultimate goal that we are predicting, or how is this information is going to be used. Mahavir, would you have anything to add to that?
No, I think that actually summarizes it very well, what you just said.
And as a follow-up on that question, so is this data available? This is something, the data that you've collected on your own, or is it freely available on various regions or countries? How does the actual data work? As in, where is that database? Is it, how do you get access to it?
There is open source data available that people can access, but whatever that data is, whoever has the data in their hand, they need to run a sanity check of how and what that data actually means. There's two things. There's having data and understanding how to read the data to find actionable insights and make correct assumptions. We use the data that we currently have on our buildings as a company, and we can stand by it because we support it with engineering calculations and years of experience. But anybody who wants to collect data or use data for their simulation needs to really cross-check that information with talking to clients, design teams, or even come and talk to us, our smart analytics team. We're happy to give suggestion and advice on this, how to go about with it. It's not a gray black box. It's out there. It's just that understanding how to use this information in the most effective manner.
Interesting. And on that note as well, on the data side, what would be an acceptable error or a standard error that you would use? Is there sort of specific standards that are available so that you can make sure your NG model is working within the correct sort of assumptions? What do you do to make that sanity check?
As far as I know, I don't think there is any benchmark for acceptable error. That said, there will always be error between what analysis, anything that you do computationally versus what you do in real terms has error. That's defined as part of the computational process. There is no real benchmark. I think what will end up happening is that as people go on and understand buildings better, the variation, I think we shouldn't, sorry, I'll rephrase this. We shouldn't call it error. We should just call it variance from expected operation. And as people understand buildings better, the variance is going to reduce. I don't think you'll ever see it go away 100%. So as long as you stick to doing the modeling in a very informed, data-driven manner, you should always be able to quantify that variance. And the ability to quantify that variance is more important than understanding what the error is itself. Where is that error coming from, or where is that variation coming from? That's more key. Because no system is going to operate at. I'll give you the most common example of why there could be variance. So you do energy modeling based on acceptable weather data that's out there. So let's take Abu Dhabi for example, and you take the HVAC data file that's generated by ASHRAE and DOE. That data is a aggregation of 20 or 30 years of weather data, and it sort of creates a most common weather profile. It doesn't account for any peaks or troughs or extreme weather events. Now, that is not to say that if I design my building on that weather data, I'll get the same weather the next year. Next year could be completely different. On March 31st, the weather file might say 40 degrees, and the actual weather might be 37. And the reverse could also be possible. So the point is that you'll always have variations. And it's only important to understand why those variations are occurring. So yeah, I don't know if that answers the question.
No, I think it does as well.
Jason, I think this opens up a really important topic. Performance gap between design and construction data has always been an issue, not just in this country, but all over the world. And I truly think that we need a platform where modelers and consultants can upload the design assumptions and construction monitoring figures as well. So we can actually have an open platform where we can share knowledge, learn from each other's data and assumptions. And this dialogue really needs to happen within the construction sector. So we can, as a collective building professionals, we can minimize the performance gap between the design and operation. Secondly, another point I would like to raise is that the world is changing and the way we design our buildings are changing. We need to upskill ourselves. So just because we have a design or an architecture, interior design planning or FM background does not mean or should not limit us. And we need to upskill ourselves in terms of data analysis, coding, and all these other parametric softwares that's out there, and really understand how we can use a cross-disciplinary approach to how we look at energy consumption for our projects, for our energy strategies, and for our buildings, and of course, energy modeling. So I think these 2 points are quite important as an industry for all of us to be aware of and implement as much as possible, and do this as a collective.
Exactly. I think that it's very important to realize that as an industry, we should evolve and learn from each other as much as we can, so that we can, as an industry, and as push the market to better performance. I totally agree with you, Farah, on that. So on that note, that's all the time we have for the Q&A session. Thank you for everyone who sent in their questions. We apologize we weren't able to go through all of them, but they were fantastic. And we really appreciate your interaction and your questions that you sent through. I would also like to thank both our facilitators from Buro Happold. Thank you, Mavia. Thank you, Farah, for this amazing webinar. It was very insightful, and I believe a lot of our attendees would appreciate your expertise on this matter. So just to wrap things up, I'm just going to, we will be sending the recording of the presentation to everyone who joined in. So thank you everyone for joining in. Please do share your feedback with us as you leave the webinar. The survey will pop right out as soon as you exit the webinar. So please do complete that, and it will help us for our future events as well. And lastly, we have a lot of other webinars for the upcoming months. So please do look at our website, to follow us on social media at EmiratesGBC, and also engage with us if you want to find out more information. So with that, thank you everyone. Have a good day ahead, and hope to see you at our next webinar. Thank you everyone. Bye-bye.